So, quick, brief discussion of angular momentum. Um, so, just like we've talked about linear momentum, P is equal to mv. We can actually define something called angular momentum, which is given the symbol L, which is going to be equal to r cross mv, and that's often written as m times r cross v. So the first thing to bear in mind is that we now have a cross product where we're going to have to look at the relative angle between the radius vector and the velocity vector. The second thing that tends to interest people is that you can have linear motion that has an angular momentum. So the classic problem is I have a rod that is set to pivot from one end, and I have something coming in. I've got an object of mass m moving with a velocity v, and so that we know that it's going to come. We know that, let's assume it sticks in there, that this thing is going to rotate upward. And we're going to look at how one might calculate the angular velocity of the rod. So that, as we've said before, as I said, the angular momentum is given by r cross v. So the radius vector looks like that. But I'm interested in what is r perpendicular to the velocity. And that just looks like the length of the rod, and I'm going to write that as a capital L. And we need to be a little careful with our L's here because I've got both an L for length and we've got L for angular momentum. So the angular momentum initially is going to look like, and I'm going to write that as L0 as a vector is equal to R, length of the rod, times the mass of the incoming object multiplied by the velocity of the object. L final is equal to I omega. And that's kind of like a definition. So we'll put that up here. This is L for a particle, and L for a system is I of the system times omega. So the I of the system would equal 1/3 m2 L squared plus m1 L squared. And now I can set this initial momentum equal to the final momentum and get a result that looks like length of the rod, mv, is equal to 1/3 m2 L squared plus m1 L squared times omega. The next problem that you'll often see is, imagine that I'm looking down on ice, and I have a rod that is set to spin, and I have an incoming mass. It's going to come and hit the rod, and then afterwards, the rod is going to start spinning. And in this case, I'm going to assume that the mass that comes in bounces back with a kind of a new velocity. So I've got a mass coming in with an initial velocity, hits the rod, sets the rod a spinning, and the mass bounces back. Typically on problems like this, since it appears to be an elastic collision, they're going to give you a final velocity of this second mass. But we can set up the usual conservation of linear momentum equation. L0 is mv0 L over 2, length of the rod. L final is, and this is where you have to be a little careful, it's going to be M, what I've called V prime, L over 2, and now I put a minus sign because it's going to the left, plus I of the rod times its angular velocity. But since this thing is not pinned, okay, it's going to also have a V center of mass. So I also need to do linear momentum. So P0 is M V0. P final is going to be M V prime minus sign because it's going to the left, plus mass of the rod, times its center of mass velocity. And these two are going to be equal. So from that, I can calculate the velocity of the rod, its translational velocity, and also its angular velocity. Typically, they'll give you, they'll tell you like V final is equal to some number. Say it comes back with half the velocity or something like that. The one last piece that's nice to remember is same problem. I have a mass, and let's assume this time the rod has a mass of M. Let's assume that I have this thing coming in here. We'll call that M1, moving with a velocity V1. But this time, after the collision, this mass here sticks. So now the piece that gets complicated here, the piece you have to be careful of is you have to calculate, the first step is to calculate center of mass. The rod will spin about its center of mass. So X center of mass is going to be M1 times 0, because it's at one end, plus mass of the rod, L over 2, divided by M1 plus mass of the rod. So that gives me some center of mass distance. I'm going to call that there X center of mass. And then now what I need to do is when I calculate angular momentum, I now need to set that up as follows. Incoming initial L0 is M V0 X center of mass. And then L final is going to be I omega. And where I need to be careful here is calculating my I. In this case, I of the system is going to be M1 X center of mass quantity squared. That's the contribution of this hunk of clay, which is located a distance X center of mass away. Then I need to use the parallel axis theorem. I center of mass of a rod is 1/12 m L squared, plus I need to do mass of the rod times L over 2 minus X center of mass quantity squared, where what I've done here is account for the fact that I have, this is the H, that's where I've displaced I've moved the pivot point from the center of mass. Having said this, everything else is still the same. We can do P0 is M1 V1 P final is, they're combined now, so M1 plus M rod times V center of mass. Again, I've taken the I of the system. This value here is equal to that value here, and I can come up with the angular velocity of the rotating object.